Okay, let's take a look at these three molecules. Now, all three of these molecules, water, hydrogen fluoride, and ammonia, they all hydrogen bond. Okay, all of them. Now, water, given that it's got this geometry, it can hydrogen bond here, here. So you have partial negative here, partial negative here, partial positive here, partial positive here. It's just a really good hydrogen bonding molecule. And so it has a high boiling point at 373 kelvins, in spite of the fact that it only has 18 grams per mole for its molar mass. Let's and now HF, it is a linear molecule like this. Fluorine is very electronegative. It is a very polar. It will hydrogen bond. Ammonia, you saw, looks like this. And these all are good hydrogen bonding molecules. So they all are relatively high boiling points relative to molecules that have the exact same shape. And what I'll use is I'll use water and its group as I go down group 6 from oxygen to sulfur. So this is just going to be hydrogen sulfide, which is nasty, nasty stuff. It's H2S, and it has the same shape as the water molecule. It's got the two pairs of non-bonding electrons on the sulfur, but it is polar. It's a polar molecule, but because it can't hydrogen bond, its strongest intermolecular force is called a dipole force. And so the boiling point goes way, way down. The boiling point is actually below the freezing point of water. And if we go down one more from sulfur, and we go to selenium down here, you have this molecule, hydrogen selenide, and this has exactly the same shape. Now, you will notice something. H2Se, that's what this is, H2Se, has a higher boiling point than the hydrogen sulfide. The boiling point is higher. And the question is, why? Is it more polar? Well, no. As we go down the periodic table, the central atom in the molecules has a lower electronegativity, so the bonds are not as polar as they are for the hydrogen sulfide. But what is happening is the molar mass of the molecules is increasing. So hydrogen sulfide, it has a molar mass of 34.09 grams per mole, as opposed to water's little 18 grams per mole. Hydrogen selenide, it has a molar mass of 80.98 grams per mole, and hydrogen selenide, it's even higher. And so what's happening is the molecules are getting bigger and heavier with more surface area. And what is increasing? London forces. The London dispersion forces, also known as induced dipole forces, van der Waals forces, that, even though it's the weakest force, it's getting bigger and bigger and bigger because the molecules are getting bigger. And that's the same explanation why you have hydrogen fluoride here, and then you go down, you have hydrogen chloride. This is HCl here. It's got a lower boiling point, but the boiling point goes up as you go further down and you get to hydrogen bromide, because these molecules are getting heavier, hydrogen iodide, because the London forces are increasing as the molar mass of the molecule and the surface area on the molecule increase. This is methane. Methane is natural gas. It looks like this. It's CH4. It's a completely non-polar molecule. You learn that in Chem 1, but we'll talk about it a little bit more. It's very lightweight stuff at 16.05 grams per mole. And here we have silane and germane and stannane. And what's happening, these are all nonpolar molecules, but they're getting bigger. And as they get bigger, the London forces cause the molecules to become stickier and stickier and stickier. And so what's happening is the boiling point for even for nonpolar molecules is going up from methane, which is way, way down here. And then if we get it here to stannane over here, it's up here at around looks like around 220 Kelvin. So which molecules are capable of hydrogen bonding? Well, you would need to know how to draw the Lewis structure if this one weren't so easy. I got to get another molecule on there. Yeah, that's your hydrogen bonder right there. CH4 is completely nonpolar. That's just CH4. It's not polar. All this molecule has going for it in terms of stickiness is the weakest force, which are London forces. CH3F, it's fairly similar to that. You've got carbon as a central atom. You've got hydrogens, and then you've got a fluorine here. Now this will be a polar molecule because fluorine is more electronegative than the hydrogens, and so the electrons will get drawn in that direction. They'll be withdrawn toward the fluorine. That's going to make this end of the molecule a little bit negative, this end of the molecule a little bit positive, and so you'll have dipole forces here. Okay? You also have London forces. Remember, London forces apply to everything, and that's their advantage. This is C8H18, this is octane, and this is a big non-polar molecule. I'll just kind of draw a skeleton of it. You've got 8 carbons strung out here, 1, 2, 3, 4, 5, 6, 7, and 8. There are hydrogens on each one of the carbons. There are 4 bonds to each carbon. It's a completely non-polar molecule, so London forces, also known as dispersion forces, van der Waals forces, these are the only forces that the molecule can exhibit. This is going to be a polar molecule, but not that much. You've got N, you've got CH3 out here, a CH3 here, and a CH3 here. So you're going to get some electron withdrawing up toward this more electronegative nitrogen. Makes it a polar molecule, so it will be polar, but it's certainly not a hydrogen bonder, and so you'll have dipole forces. Forgetting how to spell. Dipole. All right, so only water in this group is able to hydrogen bond. Which of the following should have the highest boiling point? Well, this is a polar molecule. This is an ether. This is dimethyl ether. There's a CH3 group here, a CH3 group here. You've got this, kind of looks like a water molecule. It's definitely got some polarity to it because of the bent shape and the oxygen here, but it's polar, and so it's polar, so it has dipole, but don't forget, and I should have mentioned this a little bit, I should have emphasized this in the previous slide, it also has London forces. Why does it also have London forces? Because all molecules will have London forces. Now this is my favorite molecule. This is ethanol. And so you see this OH group, the first thing you're thinking is hydrogen bond. And you would be correct to think so. So you have CH3, and you've got a CH here and a CH, and then you have this arrangement. Okay, made my oxygen a little small. Let's go ahead and throw it out there. So this is going to set up hydrogen bonding here with a partial negative and here with a partial positive. That's not as good a hydrogen bonder as water is, but it can certainly dissolve in water because water is going to love this stuff. That's why you can dissolve so much alcohol in water, because you set up this nice hydrogen bond between the OH group on an alcohol and the oxygen on a water molecule. This is propanol. It's N-propanol or 1,1-propanol. It is also an alcohol. But I want you to notice something. It's got, and every time I draw a carbon, just imagine that there are hydrogens coming off. It's got 3 carbons instead of just 2 carbons in the ethanol. And so because it's got that extra carbon, it's able to have stronger London forces. So it's going to have a higher boiling point than the ethanol does because it's got 3 carbons. It's got more surface area, it's got more mass. It's still going to be able to hydrogen bond with water. You're still going to be able to dissolve it, but this is now starting to kind of get in the way of the water molecule, because what we say is like forces will dissolve or relate to each other in solution. Like dissolves like is what we say. And the more carbons I get on here, the less like water this becomes. But we can still hydrogen bond here. All right, this is a polar molecule. This looks just like the propanol, except that, and I'm just going to use R for the 3 carbons and their hydrogens. And what you have here is that arrangement. So it's polar, but it's not that polar. So you'll have a little bit of partial positive, a little bit of partial negative here. This is going to be pretty good and negative, and this is going to be pretty good and positive. Okay, so more carbons with the same OH group mean that this is going to have a higher boiling point than the ethanol. So in terms of solubility, as you get more and more carbons, the molecule will become less and less soluble in water. So let's talk about London dispersion forces. First of all, everything has London dispersion forces, and I'll show you why in a moment. But London dispersion forces are really most important for nonpolar atoms or molecules. Nonpolar substances are the substances for which London forces are most important. We also call them induced dipole forces or van der Waals forces. So let's consider nitrogen. You are breathing it right now. It is N2. It's 2 atoms of nitrogen bound together covalently into a diatomic molecule. And it's a gas under normal conditions. However, we can condense nitrogen into a liquid. We can force the molecules together to make liquid nitrogen. How do we do that? Well, we have to remove an awful lot of energy from the nitrogen, which means cooling it down. Liquid nitrogen is very cold, The boiling point of nitrogen is minus 195.8 degrees Celsius. So that's the temperature at which liquid nitrogen boils. And shame on you if you're still thinking in Fahrenheit. That's minus 320.4 Fahrenheit. But that's the temperature at which that phase change takes place. So you really have to get nitrogen very cold in order to get those molecules to slow down enough to stick together. So if it's going to remain a liquid, there has to be some force that holds it together, and that's going to be London forces. Larger molecules tend to have stronger London forces, and so will have higher boiling points. So you can have nonpolar molecules that are larger, which will have higher boiling points than nitrogen does. So let's take a look at induced dipole, also known as London dispersion forces. So from quantum mechanics, you know that electrons, here's the nucleus of a molecule or an atom, you know that electrons never stop. They have this wave behavior, they're in constant motion, and so it makes sense, if that is the case, that you could have, and now we're sort of thinking of electrons as particles as being predominantly more on one side of a molecule or an atom than they are on the other. Well, electrons have negative charge. So you have these little tiny negative charges on your electrons, and if your electrons group together, if you get more of them just for a moment in time, a momentary partial negative charge, well, that's going to give you what we call a dipole moment. And since there's partial negative over here, the difference leaves a partial momentary positive charge on the other side of the molecule because of the asymmetrical distribution of the electrons across the molecule. And so that molecule bumps up next to another molecule and induces a dipole moment. So negative repels negative, so these electrons, they get chased to this side of the molecule, and so what we wind up with is a partial positive charge on this side, a partial negative on this side, and as long as we can keep things slowed down enough and get these molecules close enough together, put them under some pressure, that will allow this attraction to take place, and we can condense or have a condensed phase of matter even for substances that are completely nonpolar, very light, and have very low boiling points, like nitrogen. Keep in mind, all molecules have this induced dipole effect, but it's really only important for nonpolar molecules. So which of the following is the strongest intermolecular force? Hopefully that's not a big mystery here. This is going to be hydrogen bonding, and hopefully you know what arrangements permit hydrogen bonding to take place. Here's a quick overview for the type of compound. If you have a nonpolar molecule, that is, and you are supposed to know how to determine whether a molecule is polar or not from Chem 1, the only intermolecular force are the induced dipole forces, dispersion effects, London dispersion, van der Waals forces, and note it will depend on the molar mass. The bigger the molecule, the stronger the dispersion forces. Here we've got polar molecules, but not hydrogen bonding molecules. They'll have dipole-dipole forces and London forces, dispersion forces, and it depends on the polarity as to how strong those forces are, particularly the dipole-dipole forces. If you've got a polar molecule with either HF, OH, or HN, you can have hydrogen bonding, which will be the strongest. You can have dispersion forces, and we really should put dipole dipole in there as well. And hydrogen bonding is really just a super strong dipole-dipole force. But most lists will include dipole-dipole in there. So just note, has to have HF, OH, or NH to be a hydrogen bonder.